All right, so FYI, one of these examples was the exact question that was on the AP exam last year. So maybe put a star by this and say important. We know how to draw those dot structures, and we know that they have the formal charge debate where you can figure out which is the most reliable or most correct Lewis dot structure whenever you count the valence electrons that are assigned to it versus the ones that it should have assigned to it. So you can definitely see there's many varieties of how you can draw these, but there's one that is most appropriate. Well, when you have a resonance structure, you actually have two or more Lewis dot structures that are true, that are the most valid way to draw it. But you just are placing the electrons in different locations, but the formal charges are actually still the same. So a good example of this is benzene, C6H6 here. You're going to see the double bond, single bond, double bond, single bond, double bond, single bond, alternating bond system. But, you know, of course, you could easily draw on the same structure with the double bond, single bond combination on basically every other bond. So that's called a resonance structure because it's the same structure exactly, except we've drawn it two different ways. Mainly we just rotate it in a different way. So instead of saying we have two structures here, we actually say we have one superimposed, basically taking both of them and trying to blend the structures, and that blend we can draw as a hexagon because there's six carbons on the benzene, and a circle just to say those double bonds can be anywhere in here, but in an alternating fashion, single, double, single bond, double, single bond, double, okay? So the superposition that exists causes this averaging of the bond length. So single bond, which is longer, single bond or double bond? Single bond is longer, and so as you look at the difference, single bond versus double bond, and then you actually obtain data that correlates with that, you find that there's actually no, hold on, sorry, So you actually see that according to the data, the bond is neither single nor double. It's actually a combination, which is the hybrid of that. It's I'm going to call 1.5 length bond. So is that longer or shorter than a single bond? 1.5. Shorter. Is it stronger or weaker than a double bond? Weaker, because it's an intermediate strength and length between the single and double bond. So we don't say that these flip back and forth and say, oh, it's this way one time, and then this way another time, and this way and this way. It's actually neither of those structures, but that's how we portray it to say there's a superimposed way of drawing it. And that's really the reason that VSEPR, the valence shell electron pair repulsion theory, does not work all the time. That's we have additional theories on top of the VSEPR theory. What were two that you read about? Say again? Molecular orbital theory, and there's an atomic orbital theory, which we'll talk about this week. So that's why we have all these theories, and they really do a great job explaining about 70% of the things out there. But then once you find an anomaly, you develop another theory to start to explain that, which is why science is constantly progressing. So go ahead and draw the resonance structure for ozone and then for carbonate. So start with drawing one example of ozone and one of carbonate. So what's the first thing you guys are doing? Nothing? Come on, guys. Thanks, Levi. So how many electrons does ozone have? 18. Okay, and then how are you drawing it? So don't draw it so it's like so we always have to choose one central, which, I mean, we really don't have a choice here. It's got to be oxygen. And then we'll draw it with one on the left and one on the right, keeping a symmetrical structure. You would not want to put it in a triangle because those bond angles are tight. They're so unstable. That would never ever occur. It would break open and it'd be gone. But that's organic chemistry for you, so that's later. But in this case, you've used up 2, 4. So then how would you guys complete? Double bond and If I put double bonds on both sides, how many electrons do I have? So not 18? Yeah. Okay. So then give this one back. It's single bond. And then what? 2, 4, 6, 8, 10, 12, 14, 16, 18, right? Are we good? Does everyone have octet? AJ?
I think you have like a low balance
Because oxygen cannot accommodate extra electrons. It can only accommodate octet. Oxygen is a very small second energy level atom, so it doesn't have extra 3D pockets to stuff extra electrons. You guys probably saw some expanded octet on your homework, so that's why I'm sure you're thinking expanded right now. All right, yeah.
Well, having different, like you have a double bond on side, single bond on the other side, will that change your negative?
It's only the lone pair that causes repulsion, which would change the angle. So now I put the double bond. I believe I didn't tell you how to put it on. I put it on the left side. What else could we have done? Okay, double-headed arrow to say either one of these is a Dalla-Lewis structure. That's kind of the point of showing you resonance right now. Resonance is a way to describe that there are two Dalla-Lewis structures with a double bond or triple bond placed in different location. So both of these are valid, but truly what exists is a superimposed layering of these, which creates a kind of a blend. So how would I draw the blend? I draw the oxygens like this, and then I would draw a dashed line to indicate that double bond could be on either, or it's a 1.5 bond actually, not a blend. So one double bond, one single bond come together to make a 1.5 bond. Same thing, one single bond, one double bond come together to make a 1.5 bond. So I'm showing it to you like this so you understand that there's more ways that you might see Lewis structures. I'm going to put a lone pair here. It's hard to put all the lone pairs in the correct positions when you're talking 1.5 bonds. But most of the time, they would expect that you would draw this one, and then put brackets around them to say this is a full resonance system. Because this is really hard to draw sometimes accurately. So I'm just showing you this is an option, but definitely not required. This up here would be required if I were to have you draw resonance structures. Same thing, carbonate, go. Actually, this is not optional. You need to be drawing these. Carbonate was the one that was on last year's AP exam. And my students, I crossed my fingers through there, right? Because we actually did this in class. How many electrons? Say again? So what did you do with the -2? Added 2 more electrons. Okay. So carbon is 4 plus 18 plus 2 more, 24. Yeah, just making sure. I was counting in my head right. So carbon in the middle, oxygen, 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 all equally spaced apart. If I draw it like this, tell me what makes that invalid. So it doesn't have octet, right? So if I have, because I definitely could count 8, 16, 24, I've got 24, right? So that's why that's your double check, but you don't always assume you're right. You just have the structure with the correct number of electrons. So I'm going to erase this lone pair here, and then put my double bond to indicate that carbon is octet, and so do all the oxygens. I chose to put it there, but where else could we put it? Any other location. So you would have how many structures drawn to show the full resonance? 3. And to make this even more, actually to make it correct period, those are brackets, and what else on the outside of the bracket? -2 to indicate that carbonate has a -2 charge. Same thing over here, bracket, bracket's horrible, -2 charge, and then the third one would be on top up here. My dots are getting kind of skinky, but there you go. Alright, so at the same time, carbonate can show a superimposed position. So what would you do with this whole trying to figure out the length of the bond and the strength of the bond? If you take this double bond and you split it into the 3 locations it kind of coexist across, what would be the bond length or the bond that you would assign to each of these positions? 1.33. Because basically all of them have a single bond, single bond, single bond. You're taking that last bond and basically distributing it across its locations. So a third, a third, a third. So this would have a bond that's approximately 1.3 repeat, whereas the oxygen from the ozone example had a 1.5. 1.3 or 1.5, which is stronger? 1.5 because it's closer to the 2, meaning double bond. Okay, so if you're to compare these with the CO bond in carbonate or the OO bond in ozone, which would be stronger? Oxygen to oxygen and ozone. So we do specify in that molecule, so that's stronger. So which would have a greater bond association energy? Oxygen, which would have a longer bond length. Say again? The carbonate, because it's a longer, weaker bond. So there's a lot of things that can be questioned from you knowing how resonance works. Okay? Is that confusing? Yeah.
So how do you draw the
Very similar to like you have here. You would have carbon, oxygen, 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 and then dashing your lines out like that to say that second bond could be anywhere here. But really, we often don't draw it like this because it seems like it doesn't give enough information about how many electrons are actually there. Because then, like, do I put 4 electrons here or do I put 6 here? You know, because it's misleading. But it's just to show you that it could be any of those locations. The one that's 100% true is when you draw benzene like that, because that's really, you're showing it could be anywhere here, and that's a true statement. Okay, so let's get off resonance for a minute. One more kind of term to talk about is isomer. So we have 2 examples of, we have an example of an isomer here, ethanol and the diethyl ether, or dimethyl ether. Ethers is something with a oxygen in the middle, and there's something on ether side. I'm saying either as ether. Okay, cool. Just none of you are picking them out, I was putting down there. Okay, so an isomer is going to be different structure, same formula. Okay, what was a resonance structure again? Different placement of electrons, same structure. This is same formula, different arrangement of the atoms, aka different structure. So just remember there's some key terms that you should know, kind of like what are they supposed to be portraying. And since we're dealing with drawing quite a bit, you guys didn't have this in your midterm for sure because we had not drawn those dot structures, but many times they'll say, here's a formula, C2H5OH, or I could say C2, I won't even include the alcohol there, C2H6O, and they'll say, draw 2 valid structures for that. So 2 valid structures here would be ethanol and dimethyl ether, but they would then exhibit different intermolecular forces, different polarity, a couple of different characteristics that they could then elaborate on. Like this has an alcohol group on the end that can do hydrogen bonding with water, which creates a lot of attraction. This doesn't do hydrogen bonding because it just simply can't. We're going to talk about intermolecular forces later, but this would be a polar structure, but it's not going to be as polar as this one. So they start to exude different characteristics over time. But this is an example of an isomer. So then go ahead and draw, what's the name of this? C2H4. I've already given you a hint what 2 means. Are you saying E-N-E or Y-N-E? Anybody? E-N-E. So ethene. So you've got, this is ethane. Oops. Those are H's, by the way. This is ethane. And then how do you change it to the ethene? Take away 2 H's. And then do a double bond. Oops. Okay, then how do you make ethine? Y-N-E? Say again? Take away 2 more H's and make triple bond. Anes are single bonds, enes are double bonds, ines are triple bonds. And so there's a difference there in length and strength between the carbons. That's a quick review of organic, okay? right, 2 more thoughts on geometries and polarity, okay? So work with me here. I'll talk about free radicals because we actually already briefly described that. You guys saw in your structures some examples of exceptions to octet, yes? On your drawings? So we're going to talk about those exceptions a little bit, but basically octet is a suggestion, not really a full-on rule. You have a lot of things that will have 6 valence electrons, totally fine with that. Things will have more than octet, and then of course those with octet. Mainly the things that are small, like hydrogen, helium, they'll accommodate how many electrons around there themselves, 2 valence electrons. You've got beryllium and boron. You'll notice that they're kind of on the small side as well in that second group. So they're totally fine with 4 valence electrons in a covalent situation. The only thing is that beryllium, it does act metallic. So is it going to be in a covalent bond? Generally not, but it also does have a different kind of characteristic because it does act metallic, but it's got a large radius, so it doesn't mind sharing occasionally. So this one will kind of like stay away from more than the most we can because it does not act normally. Then you have everything that it does octet. Who's able to expand octet? Phosphorus and forward, basically. Phosphorus, sulfur, chlorine, argon, and forward can expand octet, meaning they can have 10, 12, 14 valence electrons and be totally fine. How and why? Because they have d orbitals that they can stuff extra electrons in. Okay, so that's kind of the overall gist of all this information. But now let's talk about the shapes these take on. So let me show you a quick video of molecular geometry, and then we'll do polarity along with this. Alright, so, hold on. Alright, so here we go.
What is the shape of a molecule? Well, a molecule is mostly empty space. Almost all of its mass is concentrated in the extremely dense nuclei of its atoms. And its electrons, which determine how the atoms are bonded to each other, are more like clouds of negative charge than individual discrete particles. So a molecule doesn't have a shape in the same way that, for example, a statue has a shape. But for every molecule, there's at least one way to arrange the nuclei and electrons so as to maximize the attraction of opposite charges and minimize the repulsion of like charges. Now let's assume that the only electrons that matter to a molecule's shape are the outermost ones from each participating atom. And let's also assume that the electron clouds in between atoms, in other words, a molecule's bonds, are shaped kind of like sausages. Remember that nuclei are positively charged and electrons are negatively charged. And if all of a molecule's nuclei were bunched up together, or all of its electrons were bunched up together, they would just repel each other and fly apart, and that doesn't help anyone. In 1776, Alessandro Volta, decades before he would eventually invent batteries, discovered methane. Now the chemical formula of methane is CH4. And this formula tells us that every molecule of methane is made up of 1 carbon and 4 hydrogen atoms. But it doesn't tell us what's bonded to what, or how the atoms are arranged in 3D space. From their electronic configurations, we know that carbon can bond with up to 4 other atoms, and that each hydrogen can only bond with 1 other atom. So, we can guess that the carbon should be the central atom, bonded to all the hydrogens. Now each bond represents the sharing of 2 electrons, and we draw each shared pair of electrons as a line. So now we have a flat representation of this molecule. But how would it look in 3 dimensions? We can reasonably say that because each of these bonds is a region of negative electric charge, and like charges repel each other, the most favorable configuration of atoms would maximize the distance between bonds. And to get all the bonds as far away from each other as possible, the optimal shape is this. This is called a tetrahedron. Now, depending on the different atoms involved, you can actually get lots of different shapes. Ammonia, or NH3, is shaped like a pyramid. Carbon dioxide, or CO2, is a straight line. Water, H2O, is bent, like your elbow would be bent. And chlorine trifluoride, or ClF,
is say again, T-shaped. This is not one you learned in honors chem. There's one called seesaw, T-shaped, square planars, and square bipyramidal. Those are expanded octet examples that you did not learn in honors chem. But that's because they're more advanced examples. So you definitely can see the T there. But why the heck is this a straight line? And why is it shaped that way? Why is it not trigonal planar? There's not only one. There's two here. And we'll talk about differentiating between is the limb here on the axial plane or the equatorial plane. And that helps a lot with visualizing it. Who's really good at visualizing stuff like this in their head? Who's a spatial person? Spatial reasoning? Some of us?
Good morning, staff and students. At this time, we will be conducting a drill, a blackout drill. Staff, if you can please follow the procedures for a blackout drill. Again, at this time, we are conducting a drill, a blackout drill. Teachers, please follow procedures for a blackout drill.
Okay.
We will make an all call once this drill is being completed. Thank you.
So, shut my back door. You guys have to go hide behind the lab stations and do not talk. Do not pull your cell phones out. Just close your eyes and take a nap. Not a word. You have to go to the left. Yeah, back where Kirk is, that side. Not a word.
blackout drill is now over. Thank you for your cooperation.
Alright, so on our way back to our desk, let's grab one of these little ones out. So, there is a, so yeah, alright, so, after, come hither, off the floor. Alright, so at your desk, I think I always have one for everybody but one. Somebody grab one first, I'll pass it out. That way we can start building a couple as we go. Grab one, come back up here. And then we'll eventually get to the last stations, but I'm not quite jumping to yet, so that's what we're back. Right. On your little kit, you should have a number. So number 1, who's number 1? Number 2. Who's number 2? Number 3. 3, 4, 5, 6, 5, 6, 7, 7, 8, 9, 9, 9, 10, 11, 12, 13, 14, 15. Alright, I'm sure we can for a second. Okay. Actually, yeah. Alright, so as a note to keep some things organized, I made that little sheet, so if you guys could fold it and just keep it in the lid for now, that sheet I just gave you. The sheet I just gave you, fold it and keep it in the lid, because I'm going to have my honors chem kids, we fold it with the writing on the outside, because they need to know that they are responsible for making sure that they counted, to note those objects are there. I've already counted these, so they should be good the way they are. But I want you guys right now to look at your, what's CLF3's name? Chlorine trifluoride on your homework that you drew, and try to build it according to the shape you know it takes on, which is T-shaped. And maybe you should compare with the plan before you claim yours as and y'all be all good. So I want to see if we're going to try to play. There's a little chart. Basically, you want to have the correct number of holes in the central atom so that it arranges itself appropriately. So just make sure you look for the correct number of holes. Since it's expanding oxide, it's not going to be black one. The black one's a carbon. Carbon for I'm going to do 4. So find one with how many holes? No. 5. Because you need 2 to represent the one pair. Alright, you have like another second to do what you're doing. What you doing? Oh. It's okay, the colors are not right.
3 is shaped like the letter T. Remember that what we've been doing here is expanding on our model of atoms and electrons to build up to 3D shapes. We'd have to do experiments to figure out if these molecules actually do have the shapes we predict. Spoiler alert, most of them do, but some of them don't. Now, shapes get more complicated as you increase the number of atoms. All the examples we just talked about had one obviously central atom, but most molecules, from relatively small pharmaceuticals all the way up to long polymers like DNA or proteins, don't. The key thing to remember is that bonded atoms will arrange themselves to maximize the attraction between opposite charges and minimize the repulsion between like charges. Some molecules even have 2 or more stable arrangements of atoms, and we can actually get really cool chemistry from the switches between those configurations, even when the composition of that molecule, that's to say the number and identity of its atoms, has not changed at all.
Okay. So you've built your T-shaped molecule, right?
Almost.
All right. Do not, let me note yourself, do not put those little bitty, teeny, tiny white things in there. They're hard to get out. So, hands off your molecules for a moment, because I know you are fiddly little people. You like to fiddle, like this. I'm funny. All right. Stop. I know. Okay. So, there are two different types of geometries. Let's discuss this before we actually build one. And I want to note it from this molecule that you don't have your hands on right now. You're looking at it. You're looking at it. Okay. So there are two different ways to think about about geometries. The molecular geometry shape are all the shapes that you've maybe noted from honors tech. I'm going to name off as many as you guys can remember. I'll start with Savannah. Any geometry you remember. Linear, okay, straight line. Bent. Tetrahedral. Trigonal planar. Trigonal bipyramidal. Octahedral. Pyramidal. T-shaped, seesaw, and so forth. Molecular geometry, there's about 10 to 12 of them. There are tons of them. Because what you do is you can look at the actual shape of the atoms and the bond. You look at how the repulsive forces of the lone pairs have done their part of switching and pushing the atoms around. So they actually have already done the repulsion. So we look at the shape that the repulsion has caused. Separately, so that's why I say molecular geometry is focused on the atoms and how they're shaped. So, water, H2O, looks like that, right? Well, I know there's two huge lone pair up here. And if I look at the lone pair and the bonds and I count 4 ligands or 4 attachments, I see that's tetrahedral, right? You see the 4? That's called electron group geometry or electron geometry because you're like, I don't care if I'm looking at a true attachment of a bond of an atom or the attached lone pair. I would consider everything equally. So we actually do count the lone pairs as electron domains, as we phrased it last week. And those electron domains, that's what I'm considering for geometry. So there's only a certain number of arrangements that electron geometries can take on. And they're the very, very, very simple ones. There's only 5. Things can be linear, counting attachments, aka ligands, and lone pairs equally. Things can be trigonal planar, things can be tetrahedral, bipyramidal, or octahedral. Notice I'm skipping all the things in the middle that would have considered how did a lone pair shift the geometry or repel the bonds to make a different geometry. So electron domain geometry only, it counts like literally everything equally. Whereas molecular geometry only looks at the arrangement of the atoms post-repulsion, after the repulsion has occurred. Okie dokie? So in terms of what you're focusing on, electrons are everything electrons. Electron domains are everything place where an electron pair exists. Versus linear, bent, trigonal, planar, pyramidal, tetrahedral. Oh, we'll talk about seesaw in a second. Yeah, you guys the only ones you guys didn't name off were the square face ones. So the square pyramid would have how many attachments? 5 true atomic attachments, and then also a lone pair on the bottom, which is what's caused that pyramid shape in form to begin with. And then a square planar is when you have 2 lone pairs, one on top, one on bottom. So we're going to be building these shortly. So how many of these do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. Okay. So let's build. Then we'll talk about molecular polarity. Because I think it makes sense to see them in front of you. Do not deconstruct until I have checked every single structure that you have built. But here's what I put online for you guys to make sure that you had a chart that would organize your findings. So you're going to have your, so just maybe the name of the compound you're building, its number of valence electrons. What was next? The Lewis dot structure. What else? Say again? Not hybridization yet. I think it's another chart you looked at. So let's do molecular geometry and then electron group geometry, because I want both geometry types. Electron group geometry is what we just talked about. There's only 5 options. Yeah, there's only 5 options. And sometimes, basically, if the, what you'll notice is we're counting electron lone pairs and bonds in the same fashion up here. If you have something that's tetrahedral, as a molecular geometry, it's also tetrahedral as an electron group because there's still 4 electron domains. If you have something that's linear in molecular geometry, it's also going to be linear here. So there are some things that will be exactly the same. I want you guys to practice with that as we go today. The next couple of areas here are, I put bond, or not bond, molecular polarity. I think that was the last thing I put. I'm going to have to look on my website. Yeah, okay. So, if you guys want to disperse to lab stations, do not mix up your substances, your kit molecules. And I want to see the structure, and I want to see them built. Oh, bond angles. That was the last thing. Sorry. And I want to see us talk about bond angles that exist there. Unless you want to sit at your desk and do that. I'm putting 30 minutes right now on the clock. Let's do 20 and let's actually see what we gotta do. I have to check off every single molecule to make sure it's right. So build, and I will come. Let's go.
Okay, first is that's what I'm looking for. I don't think so. Negative. Sorry. See? Got it. Thank you. I don't have that topic. Josh is 6 plus 8, 4, 6, 8. Yeah. I guess. That's the first one. Yeah, that's right. Yeah, you got the first one. People that write on their tummies. Yeah. Making up a system. Write it down. This is linear. This is linear. Run it, baby. Silver is silver. Here we go. Yeah, silver is silver. Next is I have no idea what they are. Who? Freshman? Sorry. You're looking at the second one. 24. 24. No. Yes.
Yeah, that's what I'm going to talk about. Yeah. That's why I'm trying to walk around, because I don't have my paper number.
Yellow. Get off. Oh no. That's so. I only have 4 right? 4. Okay, I'm gonna get honest with you. It's no problem. Because I only have 4. It works. I'm just saying that because I have my idea. I am. Look at this. 45.
What happens if I run out of things? I'm gonna come and check right now. So guys, listen up. Here's how I'm gonna make my way around. But the flexible bonds are used for multi-bonds. So if you have a double bond, you will put 2 flexi bonds on the central atom and then flex them flex them to meet the other one. Okay, thank you. I'm coming around to see your progress. But before you deconstruct, I want the whole chart filled out. Now the molecular polarity part might be the only part you're questioning yourself on, but I want to talk about this after we build.
CO2.
Hold on, I'm not ready yet. You need to hold on. I have to get my magic pen.
I don't want Okay, so this double bond, does that count as like a living?
It counts as 1 electron domain.
So there's 4 for SO3. It's 1 ligand because there's 1 double bond and there's 2 single bonds.
No.
You don't count each bond as a ligand. Okay, it's just the whole thing.
Yeah,
is
the one
ligand.
place is called the domain.
Okay, so then you just trigger. Awesome.